Of my yesterday's talk, so I made some promises. So first I wanted to explain examples of Deligne categories. So recall that we have Deligne theorem, which says that any symmetric tensor category, which I will call from now on STC, over algebraically closed field. Field will always be algebraically closed for me, of characteristic 0, of moderate growth, and so this means that the length of a power of an object is less than or equal than some constant to that power, has a fiber functor to the category of supervector spaces. So this means that it is equivalent to the category of representations of a supergroup when some element of order 2 acts by parity. And by symmetric tensor category, I remind you that I mean rigid abelian tensor category. So you cannot, I mentioned that we saw last time that you cannot drop characteristic 0, but you can also not drop moderate growth, even if you are in characteristic 0. So example of categories of non-moderate growth. So the first examples appeared actually in the paper of Deligne and Mill in their famous paper on Tanakian categories. You're going to give an explicit construction of this category. So this is a category is called rep GLT, where T is a let's say we work over complex numbers, K equals C. So rep GLT when T is in C. So it's this an interpolation of representation category of the general linear group to complex values of T. And this is also called the skein category. Well, in fact, the skein category is a Q deformation of this. Its construction is extremely simple. So let's say we have T is still a positive integer, but very large. And so we have this standard representation V. And then, so any irreducible representation occurs inside some tensor power, V to the M, V star to the N. And therefore, if we understand the category just made by these tensor powers, products of tensor powers, we can take the Karoubian completion and then obtain the whole category. So let's call this object Mn. And let us look at what is home from Mn to PQ. Well, first of all, it is 0 if M minus n is not equal to P minus Q. But if M minus n is equal to P minus Q, then we're supposed to draw a picture. So let's say this is the source and this is the target. And so here we have M copies of V. And the copies of V will be denoted by arrows, outgoing arrows. And let's say we have n copies of V dual, and this will be incoming arrows. So let's say in this case m equals 5 and n equals 2. And similarly here, let's say copies of V will be up arrows. p equal 4, and copies of v star will be the down arrows. And then if p minus q equals m minus n, then you can connect, there is the same number of arrows that are facing the line as the arrows that are facing away from the line. So we can connect them connect them completely like this. And in this category, classical category, overcrossings and undercrossings don't matter, so it doesn't matter. So we have this, and then we have this, let's say, and then we have this. So this is this is called a flat skein. So a skein is the same picture, but where you take we keep track of over and under crossings. And then if dimension of V is very large compared to these numbers, then home from Mn to Pq is the span of these flat skeins. If this m minus n is equal to p minus q. And how many of these skeins we have? Well, of course, there are a certain number of outgoing arrows, certain numbers of incoming arrows, the same number. So this is going to be n factorial, where n is that number. So this number is m plus q equals to n plus p. Let's call this r. And then there is r factorial of them. So you can say that this is the group algebra of symmetric group SR, except that the multiplication is different. Multiplication is composition here. And when you compose, you might get something that you didn't have before. So if suppose you have another skein here and you compose, well, it could be, for example, that here you would have on this side such a thing, and then you will get a loop. Loops. That's right. Yeah, that's right. That's right. And but you might get a loop, and loops are not allowed, and so you have to take the loop off. And taking the loop off, so the rule is that the loop. Yeah, so the point is that in the usual case, the loop means that we take the trace of the identity, so we compute the dimension of V, which is n in general, and here it will be t. So you just say that loop is equal to t. And so this defines a category, and it's a monoidal category because you can simply put these skeins next to each other, and it's a symmetric monoidal category because it certainly doesn't matter whether you put it this way or that way. So it's a symmetric tensor category. Well, we have to know whether it is abelian, and then so what you can do, so if you take home from Mn to itself, so which is what we are going to care about that when we take the Karoubian completion, because we will have to consider idempotence in this algebra. So this is called so Wmn of t, and so this is an algebra of dimension m plus n factorial, and it is called the Wald-Brouwer algebra. And proposition is that it is semi-simple when t is not an integer. The Wald-Brouwer algebra is semi-simple when t does not belong to z. You can actually make a more precise statement, but if you look at the set of complex numbers for which all Wald-Brouwer algebras are semi-simple, then it will be exactly all the non-integers. So, and then this means that the Karoubian completion. What?
Why is it wall? Why is it wall? Why is it
Wald-Brouwer algebra. Well, yeah, because usual Brouwer algebra is obtained if you take orthogonal group and you take some v to the n and morphisms to v to the n. So then there are some diagrams. But in the case of orthogonal group, you do not have outgoing or incoming because v is the same as v dual. But here you can draw a wall like this, and there are arrows that go up here are on the left of the wall, and arrows that go down are on the right. And then the lines that don't cross the wall, they go from one line to the other, and the lines that do cross the wall, they go from a line to itself. And so that's why it's called walled.
And the negative integers would be superspaces.
Yeah, so if you, for negative integers, you can change, you can just say that your category is generated by v, but v is odd. And that would be the same category as a tensor category, but with braiding change the sign. And that's what you would get for negative t.
That's why you have to now exclude negative.
Yeah, so there is some, so this is going to be a Wald-Brouwer algebra. And so let's say this is going to be some category C tilde. So this category, its objects are pairs of integers. And the morphisms are defined in this way. Compositions are also defined in this way. Tensor product is defined in this way. And then you can take Karoubian closure of this C tilde, which means we complete it with respect to finite direct sums and with respect to taking images of idempotence. So this is C. So this is exactly what is called the rep GLT when t is not an integer. And this is semisimple symmetric tensor category. In this category, the categorical dimension of this object V is equal to t. So in particular, it's not Tanaka. Or super Tanaka. Because in a super Tanakian category, the dimension of every object is an integer. Maybe a negative integer, but an integer. Another way to see, so this category does not have moderate growth. Not of moderate growth. And the reason is the following. So let's compute the endomorphisms of v to the n in this category. So this is just the group algebra of symmetric group. So for usual Schur-Weil, this is Schur-Weil duality. So usual Schur-Weil duality, it only holds if dimension of V is sufficiently large. It is bigger than or equal to n. Because if not, then there will be some linear dependency. What you get is a quotient of the group algebra of Sn, which is called the Schur algebra. But in this case, because of these skeins, we will have on the nose group algebra of Sn. And so this means the dimensions of endomorphisms of v to the n equals to n factorial. But there is an obvious inequality. So you have any object in your category which is the sum of mi xi, where xi are simple, then the length of x is sum of mi, and the dimension of the endomorphism algebra of x is the sum of mi squared. So we have an obvious inequality that dimension of endomorphism algebra of x is less than or equal than the length of x squared. And this implies that the length of v to the n is at least square root of n factorial, which is bigger than cx to the n for any cx, for sufficiently large n. So this has this kind of growth. So if you take log of the length, it grows like log of the length of v to the n. What you get is it's about some constant times n log n. So moderate growth means it's linear. Now we get n log n here. So it turns out that so if you interpolate symmetric groups, you also get n log n. But if you interpolate general linear groups over a finite field, then you actually get n squared growth. So you have faster growing categories. And the only rates of growth that I know that exist are n log n and n squared. So it's an open question to construct any other rate. And this has to do with the fact that these categories are more or less constructed from, let's say, finite groups. And finite simple groups. There is family of alternating groups which grow like n factorial, and matrix groups which grow like q to the n squared. So it's hard to construct anything else if you're not. I mean, we don't know how to construct these things without interpolating something. So, which upper bound? Well, there is it's easy. I mean, yeah. There is another inequality that you can use. It's not very hard. Anyway, so this is an explicit construction of this category. That's right, and that has a universal property. So it has a universal property. It means that if symmetric monoidal functors, symmetric tensor functors, or even monoidal functors, because it's semi-simple category, so nothing can go wrong here. From rep GLT to any tensor category D, symmetric tensor category D corresponds to objects X in D of dimension T. And even if this category is not rigid, this is just rigid objects with this property. So basically, we have to tell where V goes, and then it's universal, so it extends uniquely. Now, but this is all for T not integer. So if T is an integer, so we get only a Karoubian category. Because this algebra isn't semi-simple, so when we take images of idempotents, we do not get a semi-simple category, and in fact, we do not get an abelian category. So we get only objects which are indecomposable direct summands in such tensor products, and not all representations can be obtained in that way. So the question is how to construct a abelian envelope. And another, which means embed this into an abelian category and add all the representations that are missing, which do not occur as direct summands in this tensor product. And the related question is, what about characteristic P? Can we construct non-moderate growth examples in characteristic P? Well, in characteristic P, you can still do this, and you can still obtain a Karoubian category. But this Wald-Brouwer algebra is actually not. So there is no values of T in the ground field for which all these Wald-Brouwer algebras are semi-simple. So you will never get an abelian category. You always get a Karoubian category. And also, you cannot actually. So this category is not embeddable. So in characteristic P, if T does not belong to the prime field Fp, then abelian envelope does not exist. Because there exists an nilpotent endomorphism whose trace is not 0. We discussed that last time. This endomorphism was the following. We took V to the P, and we took the cyclic permutation. and this endomorphism was 1 minus c. So so actually, both of these problems can be dealt with another approach to constructing this category, which uses some model theory and which uses construction through ultra products. So let me try to. No, there is no construction. There is a construction for just additive categories, but not for tensor categories. Yeah, so this is I haven't actually tried. It's and this is related to some other setting where I really want to do this because I have no construction. So I haven't tried this, but this could work in the situation when it exists. But so what we will see that in fact, so if T does not belong to FP, then there is no abelian envelopes. But when that's already seen. But if T is in FP, there are actually infinitely many abelian envelopes which correspond to liftings of T to a p-adic integer. So I will explain this. But first, let me explain some model theory about which I don't know anything. So I will explain the definition of ultrafilter. Actually, I used to be scared to death of this word. And when I heard it, I immediately winced. But then I learned that it is something that you can explain to a kindergartner.
To a Russian high school student.
What?
To a high school student in Russia.
Yeah. So that's definitely you can do that. So what is an ultrafilter on a set X? So this is a subset F in 2 to the X, a set of subsets of X. So so these are going to be sets that are almost everything. So when we say something holds almost everywhere on X with respect to F, that means that the set of points where it holds is an element of this F. And there are just 4 simple axioms. So first axiom that the whole set is in F. So everything is almost everything. Then the second axiom is that exactly one of X and its complement are in F. Some set and complement are in F for S and S. So sets that are not in F will be called almost nothing. So if the set is almost everything, its complement is almost nothing, and vice versa. Then there is so if you have a set S containing T, and T is in F, then S must be in F. So if you have a set which is almost everything and you add elements to it, then it's still almost everything. Yes. And last axiom is the following, that if 2 sets S and T are in F, then the intersection of S and T is in F. Or equivalently, if A and B are not in F, then the union of A and B is also not in F. So if you have 2 sets which are almost nothing, then their union is still almost nothing. Now, what kind of ultrafilters exist? So do they exist? Well, there is an obvious example, which is so-called principal ultrafilter. which I call narcissistic ultrafilters. Because principal ultrafilter is the following. You pick some element of X, and then you say that a set S is an F if and only if it contains this element. So a set of people is almost everything if it contains me, and almost nothing if it doesn't contain me. So, but these ultrafilters are boring. So narcissistic people are normally rather boring, and similarly narcissistic ultrafilters. So the question is, do there exist others? And then the answer depends on whether you believe in axiom of choice. So you can only prove existence of others. So not finite sets, there is no others. You can prove very easily that this is the only thing. But on infinite sets, if axiom of choice implies that there exist non-principal ultrafilters. So axiom of choice, there exists non-principal ultrafilters on infinite, on any set. And it's a series, it's uncountable axiom of choice, even if you want ultrafilter on the integers. Huh? On any infinite set. But also on any, well, on any set, on any infinite set, yes. Okay, so now what are they good for?
You use L(1) axiom of choice to get ultrafilters on all infinite sets, or how does it work?
No.
L(1) to get it on countable
So like countable axiom of choice is not enough. You have to use uncountable axiom of choice. Even, well, I think you have to use it for sets like this. But I actually never studied the foundations of this subject. But what are they good for? What? So they're actually quite useful to make various non-constructive proofs. No. Complements of finite sets do not satisfy these axioms. Right, because complements of finite sets do not, if you have a set which is infinite and its complement is still infinite, then it doesn't satisfy condition 2.
It used to show that there are multiple symmetries that don't satisfy the axiom of choice.
Yeah. So if you don't believe in axiom of choice, then you're stuck. So
No, because if Zermelo-Fraenkel set theory is consistent, then axiom of choice is consistent with Zermelo-Fraenkel set theory.
Okay, but anyway, I gave this talk, this type of talks in the presence of Dror Bar-Natan, and he doesn't. He said that this is all bullshit because axiom of choice is wrong, and yes. Don't tell this to him. He can get violent. Anyway, so what are they good for? They are good for the following: that if you have any kind of category, so let's say you have sets with structure. Let's say sets or groups or rings or fields or whatever you want. Then you can define, so let's say x1, x2, x3, and so on. So there are sets, groups, rings, fields, whatever you want. Let's say F is a non-principal. Question? Yeah. Ultrafilter on natural numbers. Then you can define the ultra product over I in F, xi. And that's an object of the same category. So what is this? As a set, it consists of sequences x1 and x1 x2 and x2, and so on, modular equivalence relation such that sequence xi is equivalent to xi prime if xi is equal to xi prime for almost all I with respect to f. So doesn't just mean for all I, but finitely. It doesn't mean for all I, but finitely many. But it means that the set when they don't coincide is almost nothing. And because of that, we don't even need this xi to be defined. So xi can be defined not for all I, but for almost all I. Yes, I'm sorry, with respect to f. So they don't have to be defined for all I. They can be defined just for some almost all I. And in particular, if a small set of factors are empty, this doesn't affect the product. So if you but you can also do it with categories, small categories. Then you have to do objects and morphisms again are morphisms between two sequences of objects defined almost everywhere, and two such sequences are the same if they are the same almost everywhere. And so this is a way to construct new things. So for example, let us consider the product of over I in n with respect to f of some set S, which is a finite set. Well, then I claim this is S. Because what happens is that there are finitely many points in S. And so if you have a sequence, then it takes values in S. But the ultrafilter is going to vote for one of them. So the pre-image of every value is a subset. And these subsets, this joint union of them is everything. So that means that exactly one of them is almost everything, and everything else is almost nothing. And so the ultrafilter votes for one of them. But if you take infinite sets, that's not going to be the case, and you will get something much larger. In fact, always uncountable. So for example, let's consider a product over I in n with respect to f of, let's say, we put field of algebraic numbers. So what are we going to get? So we're going to get a field. Why is it a field? Well, so suppose you have an element that is not 0. That means that it is not 0 almost everywhere. So that means we can invert it almost everywhere. And where it is 0, we cannot invert it. But we don't care because values almost nowhere don't matter. Values which are almost set, which is almost nothing, don't matter. So it's a field. It has characteristic 0. Then it's algebraically closed. So actually, these are all properties of first-order logic. And they go along for the ride when you take the limit. The only things that don't go along for the ride is various statements which contain the word finite. For example, if we take an ultra product of finite sets, this is not necessarily finite. If these sizes of these sets grow, then the limit will not be finite. And it is algebraically closed, and it has cardinality continuum. But then there is a standard theorem that any field with these properties is isomorphic to the field of complex numbers, non-canonically. So we get the field of complex numbers. Now, suppose we take product over I in n, f, algebraic closures of finite field, where this is the ith prime or actually more generally any sequence of primes that goes to infinity? Well, it's a field. It has characteristic 0 because the characteristics here grow. And it is algebraically closed, and it has cardinality continuum. So this is still C. So this allows you to go between characteristic P and characteristic 0. OK, so now, but you can also do this for categories. So that's the whole reason I mentioned it. So yeah, no, this isomorphism is also non-constructive. It's like isomorphism between algebraic closure of p-adic field and complex field. To construct this isomorphism, you also need axiom of choice. And it's not unique. So it's unique up to action of automorphisms of C, but there is no choice that you can actually explicitly construct. Anyway, but
Can I use this case number only once?
No, because they still differ by action of automorphisms of C. And automorphisms of C is, you cannot construct, except complex conjugation, you cannot construct any of them using, without axiom of choice. So, but anyway, so what I want to do is I want to consider categories. So let's take Ci, which is Cn, which is representations of, let's say, GLn, let's say, over Q bar. Or we could do C. If you replace Q bar with C, then it is still going to be C. So because it still has cardinality continuum. But it will be a different C, a bigger C. Anyway, so let's take these categories, and let's take the product over n in n with respect to f of Cn. So this is going to be a huge, so this is going to be a symmetric monoidal category. Because these properties go along for the right. Also, it's going to be abelian. But what it is not going to be is Artinian. Because this is a property of having finite length. And finite is a forbidden word. So in fact, there will be objects of very infinite length in this category. So this whole category is too big. But what we can do is there is an object V in this category, which is the sequence. So which is the sequence of Q bar squared, Q bar cubed. This sequence. And then if you look at the, so this is the vector representation. And the point is that if you take a tensor product of a fixed number of copies of this representation with its dual, then morphisms between such things, their dimension doesn't grow when the dimension of this representation goes to infinity. And for that reason, in this particular case, this object generates an Artinian subcategory. So, so proposition, the tensor subcategory generated by V is tensor subcategory generated by V is Artinian. So it is a symmetric tensor category. And it's actually also semi-simple. Because again, this is something that goes along for the right. Now, what is this case? So I claim that this category is, so this is in Deligne's paper. And the claim is that this category, let me call it C, sits isomorphic to rep GLT. But then the question is, what is t? We didn't have any t. So in fact, a priori, this category depends on the ultrafilter. And if it did really depend very seriously on this ultrafilter, that would be a very bad news. Because ultrafilter is extremely, it's non-constructive thing. It's like a black hole. We cannot extract any information from it. And so if it really depends on it, that's a bad news. That means that we cannot do anything with this thing. But it turns out it depends on it in a very mild way. So it really depends only on some number t, which you can extract from it, or rather extract it from this isomorphism. So what is this thing? So we have we have this number t, which is 1, 2, 3, and so on, inside this field, the product of q bars. And this number, so what kind of number is this? So this is a transcendental number. Why is it transcendental? Because if it were algebraic, it would satisfy some polynomial, but there is no polynomial with rational coefficients satisfied by all these numbers. And so it's a transcendental number. Now, which transcendental number? Well, any that you want, because remember, we have to fix, in order to really talk about this as a number in the complex field, we have to choose this isomorphism. And this t will go to some number under this isomorphism. But all transcendental numbers are conjugate under the automorphism group of the complex numbers. So that means that we can choose whatever transcendental number I give you, let's say pi or e or whatever, you can always make an isomorphism that will produce this number. So this for transcendental t, this is reconstructs no, it is C-linear. I mean, well, I mean, if you make this isomorphism, yes, that's right. Or you can say that t is a variable, and so you can say that you're working over c of t bar, but this is still c, so you're still going to be getting the same thing. And t under this isomorphism goes to some transcendental number. So anyway, so that's part of the story, because what happens for algebraic numbers? Well, for algebraic numbers, you can do the same thing, but you should use limit from characteristic p, as explained here. So so here is a construction. So suppose that t is in q bar, but not in z, let's say. And then we have to choose, well, actually you can also be in z. This is going to produce something. And then you can take, so let's say it has a minimal polynomial q of t, q of x, q of z. And then we choose a sequence of primes. Pi goes to infinity of primes such that q has a root ti in fp. So it is easy to show that such sequence exists for any polynomial. And then what you do is you just take product over I in n over f of what? This is easier. This is easy. Huh? You can. There is a one-line proof. Yes. So the product is over f of pi of the categories of representations of GL Ti of f pi bar. And so, and then there is an object here which is the same thing, like V1, V equals to, well, V1, V2, V3, so the vector representations. And you can show that this generates a subcategory of finite length, so Artinian, and it is equivalent to this rep GL T. Well, except that really you have to choose that isomorphism, and instead of T you might get a Galois conjugate of T. But by choosing the isomorphism you can always get whatever number you want. Well, it's not clear from this why this category is semi-simple when we are away from Z, because these categories aren't semi-simple. And in fact, if T is an integer, the category isn't semi-simple. But the good news is that we constructed the Deligne category this way, even for integer T, which is abelian. So this is an abelian envelope of the Karoubian category that we had. They will grow so that's right. Ti should go to so Ti. So let's say Ti. We have Ti twiddle are lifts of Ti to Z plus, and they have to go to infinity. That's right. Yes. It's just a category of finite dimensional representation of this algebraic group. Yeah. So, so we do get some abelian envelope, but what is bad? So this approach, the problem with this approach is that you can never. It's very hard to prove any kind of universal property when you construct something this way, because a priori it depends on this f and so on. And now, but the good thing about this approach is that you can also use it in characteristic P. So let's say suppose we want to remain in characteristic P. And let's take the product over I in F in N with respect to F of Fp. So I lied. I don't want to get a very large field, so I'm going to take just the product of Fp and work over algebraically non-closed field. It doesn't matter in this case. And so then, right, so this is still Fp, and then I'm gonna take so I'm gonna take the product over I in N with respect to F of representations of, let's say, GLN. Over Fp. Okay, let me just take Fp bar just to be safe. So this is going to be some field in some big field, but of characteristic P. Okay. So and then I'm going to take this this product, and then so there is this standard object V in there, and the question, and I'm going to take the category which is generate. So this is an abelian tensor category. No, algebraic group. Yeah. Okay, so so we have this category generated by V, and the question is, what do we get? So how much does it depend? How much does it depend on the ultrafilter? Well, and for this, so well, one thing we can extract from it is the dimension of V. So this is a parameter that we can extract from the ultrafilter. So what is it? Well, for each of these, we will have some dimension. Well, dimension n, which we should reduce mod p. We will get some number in fp. So we get a sequence of elements of fp, which is just 1, 2, 3, so on. P minus 1, 0, 1, 2, 3, p minus 1, 0, 1, 2, 3, p minus 1, and so on. And the ultrafilter is going to choose, so this, it's going to vote for one of those values. And this will be our dimension. So that's one parameter. But actually, it depends on more. So it's an element of fp, yes. So I explained that last time. You take, if you have a symmetric tensor category in characteristic P, then dimension of every object must lie in fp. That's a difference from characteristic 0, where it could be anything. So if you have a cyclic permutation, x to the p to itself, you have 1 minus c. That's right, but this is a abelian category, so it's okay. So this is 0. And this means that the trace of 1 minus c must be 0. But trace of 1 is dimension of x to the p. And trace of c is dimension of x. So we get that this is 0. But actually, it depends on more. So what you can do, so in characteristic P, this dimension must lie in Fp. But we have more information, because if you have pth exterior power of V, then in characteristic 0, its dimensions of all exterior powers are just binomial coefficients. But in characteristic P, the dimension of this thing is not determined, because binomial coefficient doesn't make sense. So this dimension is actually independent of this. So we have this T0. And so this is T1. And then we can look at dimension of wedge P squared of V. And then this is T2, and so on. And all of them are in Fp. And then we can form the p-adic integer T, where T is equal to T0, T1, T2, and so on, which is like T0 plus T1 times P plus T2 times P squared plus so on. And this T is extracted from here. digits. So these are digits of this periodic number. That's right, yeah. So, so
If you take the exterior powers, symmetric powers.
I'll say about that. So this is one of the options. So in fact, there is a theorem that we proved with Harman and Ostrik. Which says the following. If C is a symmetric tensor category in characteristic P, then and X is an object in C, and you write the sum over n equals 0 to infinity of dimension of wedge n of X times z to the n, then this is equal to 1 plus z to the d, where d is a uniquely determined periodic integer. So this means is exactly that these the dimensions of all exterior powers are determined by the dimensions of only exterior powers of degree 1, p, p squared, and so on. What? Yeah. D depends on x. And so this dx is called the periodic dimension of x. So this is maybe I should call it tx, because this is the same as this t. And but Ezra asked what happens with symmetric powers, and well, you can also do this for symmetric powers. So you can consider the sum over n equals 0 to infinity of dimension of symmetric powers, Sn x times z to the n. And this is going to be 1 minus z to the minus tx, but prime, where this does not have to be equal to tx. So tx is not equal to tx in general. It is going to be equal in this category, but in the Verlinde category it is not. And this is related to failure of exactness of the Kazul complex in the Verlinde category. No, no. In good cases it is, but in bad cases it is not multiplicative, and not even additive on short exact sequences. But it is defined. So, and you can talk about it in the following way. So how do you extract this from the ultrafilter? So there is the following fact. So of course, suppose you have X, which is a compact metric space. And suppose xi is a sequence of points. Well, then we learn in the first course of analysis that this sequence has a convergent subsequence. But it doesn't have to converge. However, if we fix an ultrafilter on n, then it turns out that it votes, so it has many subsequential limits. It could be all the points of x. But it turns out that the ultrafilter votes for one of them. So there exists a limit of xi when I goes to infinity with respect to f, which is a point in x, which is one of those subsequential limits which is preferred. And that is the point such that any neighborhood of this point contains almost all members of the sequence, but now in the sense of f and not in the sense of usual analysis. And you can show that this point exists, and it is obviously unique. You can show that it exists by the standard Heine-Borel argument. Like if you have, for example, a line interval, you divide it in two parts, and then almost all points are in one of the parts. Then you divide it in two parts again, and almost all points are in one of the parts, and so on. And so in particular, we can take x equals to zp, periodic numbers. And we have a sequence 1, 2, 3, and so on in zp, the sequence of all integers. This sequence is dense, and its subsequential limits are all points in zp. However, the ultrafilter wants for one of them. So limit of n, when n goes to infinity with respect to f, is equal to t, which is an element in zp. And that's exactly the t that you will get from this procedure. And the theorem of Harman, which was conjectured by Deligne, in his letter to Ostrik, is that the resulting category depends only on this t. And the p-adic dimension of the standard object will exactly be t. So t is recovered, but this is the only information that you need from this ultrafilter. And of course, to do this, you have to construct this category in a more explicit way, which is what Harman actually did. So he used the fact that modular representation theory of the symmetric group has periodicity patterns with respect to powers of t. Powers of p.
What are the assumptions for the setting of this theorem? So you have some category.
No, for this rep GLT. So we get. So we just do this thing. So you take there is an ultrafilter that a priori this depends on. Now the theorem is that it only depends on that number t, and then we can forget about the ultrafilter.
So it depends on those FP numbers.
That's right. They are the digits of this t.
So rep GLT has changed meaning, so t is now p-adic.
That's right. In characteristic p, t should be a p-adic number, p-adic integer. Okay, so this is somehow first part of the story. So any questions up to this point? Okay, so now I wanted to talk about, again, yeah, this category is very much non-semisimple for any t. And in fact, it is an open problem whether there exists a semisimple category of non-moderate growth. This category has non-moderate growth. But it's not semi-simple. Actually, it is interesting to study it, but it's a kind of a interpolation of modular representation categories of GLN. And there is a similar category for symmetric groups, which is also not semi-simple for any t, also defined for p-adic integer t, and so on.
So these are abelian envelopes, and you don't know that these are all abelian envelopes.
Yeah, the conjecture is that the only abelian envelopes are defined by liftings of T0 to, well, there is actually a series of Karoubian categories. So if you take a Karoubian category, which is generated just by V and V star, then it contains all the exterior powers up to degree P. But then the Pth exterior powers is not a direct summand in the tensor product, and so you don't get it. But you can artificially add it and consider this web category or so on, which has this exterior power. But then the exterior power degree p square won't be contained. So the first category depends on, so actually Karoubian category depends on just a parameter in your ground field, not necessarily in FP. Then towards the next step, to add wedge p, you need the first digit to be in FP, but the second digit could be any number in the ground field. But if you want to go to the next level, the second digit has to be in FP, then the third can be anything. If you want to go to all the levels, then all the digits have to be in FP. Okay, so now I want to talk about semisimplification again. and modular representation theory. So, recall that we have some tensor category C, then it has n, which is negligible morphisms, and then these are morphisms F such that for any morphism G the other direction, the trace of the product is 0. And then you can define C bar, which is C mod n. This is a semi-simple tensor category whose simple objects are indecomposables of C of non-zero dimension. So in particular, this can be applied to the following problem. So suppose you have a G is a finite group. Let's say a finite P group. And actually, we will consider representation theory of G in characteristic P. Actually, even if G equals to Z mod 2 to the cube, it is already a hopelessly difficult problem because it's a wild problem. Also for Z mod 3 squared, it is very hard. And let V be an indecomposable representation. Of course, the reducible representations are trivial because every reducible representation is one-dimensional trivial representation because it's a P group. But the indecomposable representations are very complicated. So let's take an indecomposable representation and let us say that it has a dimension which is not 0 mod P. For example, for P equal 2, this means that you will take an indecomposable of odd dimension. And then you want to take a tensor power, let's say, and then you ask how many indecomposables of dimension not equal 0 does it have as direct summands. So this decomposes in a direct sum of indecomposable by Krull-Schmidt theorem in a unique way. And some indecomposables have dimension 0 and some don't. Actually, it would be more interesting even to know how many indecomposables you get at all altogether, but that's very hard. So let's just focus on the representations that have dimension non-zero mod P. Let's say odd dimensional. So for example, there is a Benson's conjecture which says that if P equals 2, then just 1. Well, we have to get at least 1 because the dimension of this thing is the nth power of the dimension of V. So it is not, it is still odd if V is odd dimensional. But the Benson's conjecture is that you only get 1. And this is checked by a computer in a lot of cases for this group, for example. And but still, we have no idea how to prove this. And then, so what?
Decomposing powers of a given that is not a wild.
Well, this is not a wild problem, but this is still a very complicated
I know
problem.
it's complicated, but somehow it's not wild.
No, there is a hope to solve it, and it has a lot to do with what I was talking about, but it's still very hard. So, so what does it say in terms of semi-simplification? So let's consider rep G semi-simplified. So then this will be a semi-simple category whose simple objects are indecomposables of dimension not equal to 0. And so this is really a problem about decomposing V to the n in that semi-simplified category. So what this really says is that, so Benson's conjecture is equivalent to saying that rep of G bar for characteristic 2 is pointed. So every simple object is invertible. So let's see how close we can get to proving this by using this theory that I've been talking about yesterday. Well, so question?
How many indicators do you have in total?
Well, I mean, there are, of course, infinitely many indecomposables, and they actually, if your ground field is uncountable, there is always uncountably many indecomposables. But of course, if you decompose tensor powers of V, you can only get countably many indecomposables. No, because in every dimension there are indecomposables, and they depend on many parameters and the growing number of parameters. So, so let's see how close we get to the proof if we use this theorem. So let me remind you Ostrik's conjecture. Any semisimple symmetric tensor category of moderate growth in characteristic P admits a fiber functor to where P. This is a theorem if the category has finitely many objects. If the category has finitely many simple objects. Now, so what does it say for P equal 2? So there should be a functor from our category to where 2, which is just the category of vector spaces. This is equivalent to saying that C is a representation category of G, where G is an affine group scheme. Moreover, it's a semi-simple affine group scheme. So it's a affine group scheme whose representation category is semi-simple. Now, actually, in characteristic P, so this is what is called linearly reductive group, linearly reductive. And it's much stronger than reductive. So in characteristic P, reductive groups look much simpler. In fact, you can only have a torus and a finite group and a finite scheme combined. Because ordinary reductive groups such as SL2 and so on, they are not linearly reductive. Their representations are not semi-simple. So that's very helpful. So in fact, there is a theorem.
Can you show that terminology? I thought linearly reductive means satisfies non-limit conjecture. Which all reductive groups do.
No, linear reductive means the category of the
Yeah, this is called Mumford conjecture. I think it's called power reductive. So it's about lifting of invariance. So so if you have a ring with the action of this group and an ideal, then well, in linear reductive case, you can lift any invariant in the quotient to an invariant in the original ring. But here the theorem is, it's a very powerful statement that you cannot necessarily lift an invariant, but you can always lift some power of it. And this implies all kinds of things like Habush's theorem and so on. So the theorem is the following, that I think it's due to Nagata. It's an old theorem. And it says that semi-simplified group scheme looks as follows. So you have a torus. So this is a torus. And then you times it with A, and this is a dual scheme to abelian P group. Abelian 2 group, let's say, well, P, it's for any P actually, P group. And then you can act on it by gamma, and this is a P prime finite group, finite P prime group, which means it's of order relatively prime to P. So it acts on this and on this, and you take the semi-direct product. And so, so what Benson's conjecture is equivalent to saying, and then the semi-simplification, C bar, is going to be just represent. So then it will say that it's a representation category of this G. So if Ostrik's conjecture were true, this would mean that C bar will look like representations of this kind of scheme, which is a very simple thing actually. No, it doesn't have. So no, that's why I'm saying, huh?
Your P category has finite
No. It's a conjecture which is proved in the case when it has finitely many simple objects. But let me assume that conjecture is true, or assume that I know that I can only get finitely many simple objects if I tensor V with itself and even with its duals. Finitely many objects of non-zero dimension, if I can get. So this is called algebraic representation, and there are such representations. So let's assume that I have one of those, or that I know this conjecture. So then P prime group. So this means it's a group of order co-prime to P. And this semi-simplification is going to be rep G. So this Benson's conjecture is equivalent to saying that this G is abelian. Because that's a statement that all irreducible representations of G are one-dimensional. So in particular, if we knew, so in fact there is a stronger conjecture that gamma equals to 1, also of Benson. So conjecture is gamma equals 1. And also, we don't know any example where A has 4 torsion. So A seems to always be an elementary abelian 2 group, dual to elementary abelian 2 group. Torus you can get of any rank, actually. No, this is Benson's conjecture is equivalent to the statement that G is abelian. Yeah, so if you start with a finite 2 group, so Benson's conjecture is for 2 groups. So if we start with a finite 2 group and take a representation, indecomposable representation, and generate a category with it, in the semi-simplification, the category is going to have all simple objects invertible. So we do not understand why, so Ostrik's conjecture I believe, but I don't understand why this group has to be 1 and why you cannot get non-abelian. So maybe, actually maybe we didn't do computer search far enough, but Benson actually spent many hours and wrote a very nice program. So I have very little doubt that it is true. So maybe there must be a reason why this group is always 1. But many examples, and it's so another but what we already get from this, if we know that this statement is true, is that how this thing will grow, because of course in this category, whatever these groups are, it is easy to compute the growth rate of tensor powers, how the length of tensor powers grow. And so, for example, you get that the length of v to the n for any v is going to be equivalent to some constant times d to the n, where d is an integer. So d will be the dimension of the image of v in the semi-simplification. Conjecture is that it is 1 for p equal 2, but for p greater than 2, it is not 1. And it actually... so actually, it's not integer. It's a quadratic. It's a quadratic. So it's going to be a dimension of some object in the Verlinde category. So it's going to be some number, algebraic integer in the cycloatomic field, Q of zeta p. But for d integer, for p equal 2 and 3. So this much we get from it. So if you p equal 5, you no longer, this is no longer maps to vector spaces. It maps to the category Verlinde 5, and so you get so you get some scheme in that semi-simple group schemes, and this raises a question: what are semi-simple group schemes in the Verlinde category? There is a conjecture of Ostrik about that, which is very nice.
Actually, can I say there's no counterexample known to Ostrik's conjecture?
No. To this one, no.
What was the one that was
False? Well, the same conjecture for non-semi-simple categories. That's false. So let me explain Ostrik's conjecture on what are the semi-simple fusion, what are fusion categories in characteristic P.
Sorry, so assuming the Ostrik's conjecture, you're given that two group, can you write down the corresponding algebraic group?
No, it's not so simple. Well, for example, one question is, what is the dimension of this torus? That's not such a simple question. No, I don't know how to do that. It's finite, I know, and it can be any number, I think. But there is also a question, for example, when you tensor this V with itself in the semi-simplification, of course, we just get one-dimensional things. But if you tensor this V with, but the corresponding odd-dimensional indecomposable, of course, has growing dimension. The question, how does it grow? You get some function on this lattice, which is lattice of character of this T. And what kind of function is that? So that's also completely mysterious. So let me explain what is Ostrik's conjecture on classification of linearly reductive group schemes in Ver P, which I remind you that Ver P is the semi-simplification of the category of representations of Z mod P in characteristic P. So, let's think about what kind of categories we can construct. So let me, for this purpose, I should first mention that there is another construction of this Ver P which has to do with SL2, because its tensor product was given by Verlinde rule, so which comes from SL2, and so there should be a construction of that from SL2, and this is how it originally came up. So this Ver P is Ver P of SL2, which is the category of tilting of SL2 of FP in characteristic P divided by negligible objects. So this tensor ideal of negligible, so this category is Karubian, But it is a subcategory of an abelian category, and so trace of an nilpotent endomorphism is 0 there. So we can run the semi-simplification procedure. But the negligible ideal of negligible morphisms is in this case a thick ideal. So any negligible, so it is the same as the ideal of morphisms that factor through a negligible object, which is an object whose dimension is 0. So you can just mod out. That's not true in this case. So here there are some morphisms that are negligible, like morphisms for p equals 3 between one-dimensional and two-dimensional Jordan block. So this is negligible, but it doesn't factor through a three-dimensional, which has dimension 0. But in this case, it's true. So you just mod out by negligible objects, which tiltings are numbered by positive integers, and you just mod out by all numbers starting from p minus 1. So you get 0, 1 up to p minus 2, which gives you p minus 1 objects, which I explained. And this procedure you can do for any group G. So you can define ver P of G, where G is, let's say, a simple group, algebraic group. So you want to consider P greater than the Coxeter number. So in this case, we know exactly which tiltings are negligible, and you take a quotient, and this is this category ver P of G, which is a reduction mod P of some category that comes from conformal field theory. And so then you can, so this category is a semi-simple fusion category, so it has a fiber functor to ver P of SL2, which corresponds to restricting representations to principal SL2 subgroup. And so we have these, so we can tensor them together. So we can tensor these ver P of Gi. And then we can also tensor this with a pointed category, which means every object is invertible. So this corresponds to this torus. So we can always have a torus, and we always have this thing. And then we can equivariantize it with respect to some p prime group. So if you equivariantize with respect to a group that that has order of co-prime to p, then it is still going to remain semi-simple. And Ostrik's conjecture is that this is the only thing you can get, provided that you include the case. So there is a super group which has semi-simple representation theory in characteristic 0. So this should include OSP of 1 to n when p is greater than 2n, I guess. So this is the conjecture. So what it says, for p equal 2 and 3, it really reduces to this kind of statement. And so then it is Nagata's theorem, except in characteristic 3, you also can have super space. So there is some signs that are involved. But in characteristic 5, we get, the only group we get is, so characteristic 5, we have to have Coxeter number less than 5. But of course, if we take, there is also this thing which is called level rank duality, which says that SL2 in characteristic 5 will give the same thing as SL3 in characteristic 5. In general, SLN in characteristic 5, when n is less than p, SLN in characteristic p gives the same thing as SLP minus n in characteristic p. So that means SL3 won't give us anything new. And in fact, the only thing that you can get there is SL2 or OSP21. But OSP21 is actually, turns out to be a product of two SL2s, equivariantized with respect to Z mod 2. So in characteristic 5, the conjecture, this is the first case where this is not known. And the conjecture says that any such category looks like this. So you take a product of Verlinde 5 to the R times pointed category. And this is equivariantized with respect to some gamma. So this means that the picture is the same as here, except that we have to add, besides torus, we have to take the fundamental group of Verlinde 5 and raise it to some power. So there is another factor, which is that. So anyway, so this is the conjecture. And this actually should, you might ask me what happens if P is less than the Coxeter number. And when P is less than the Coxeter number, actually this problem is very interesting. What do you get when you take tiltings modular negligibles and modular negligible morphisms? And in particular, which tiltings have dimension not divisible by P? And what are these dimensions? So as people know, especially Jordi, computing dimensions of tiltings, even for SL3, is a very hard problem. But, right, it's still open, yes? Huh?
I agree.
Even for SL3, it's open, yeah? But it turns out, but if you want to compute dimension modulo P, then it's actually a much easier problem. And this can be treated through the theory of semisimplifications. So because dimension modulo P is the same as dimension of the image of your object in the semisimplification. And so you just need to understand semisimplifications of category of tiltings for some group G in characteristic P, where P is, let's say, less than or equal than the Coxeter number. And so this is a very interesting problem, and we're, with Ostrik, we're writing a paper about this. We completely understand the case P equal 2 now, where all of them are, where you get a pointed category. So we know exactly which ones have even dimension and which ones have odd dimension. And then, in general, this should reduce to some kind of analysis of these Verlinde categories. So, so we have some guess of what this thing looks like. And this should ultimately give a closed formula for those dimensions, modulo P. I guess this is probably enough. Okay, thank you very much. I think for 3 groups you get a Z mod 2 sometimes. As far as I remember from the examples that Benson computed. But I'm not sure. This was 2 years ago that I talked to him about that.
Is it to produce a finite concept from semisimple category?
No. So from a semisimple category with finitely many objects to this Verlinde category. So this is proof of Ostrik's theorem. So maybe I'll explain the idea. So the idea is very beautiful. So what you do is so suppose you have a semi-simple category, which we don't assume to be finite for now, in characteristic P. And then what you can do is you can produce a Verlinde, so you can produce a Frobenius functor. So this is a remarkable idea of Ostrik, where this is a product with Verlinde P. And this functor is defined as follows. So you take an object X, then you raise it to power P, and this lies in C box times with representations of ZP, because ZP acts by cyclic permutations. And from this there is a semi-simplification functor into C times representations of Z mod P bar, which is C times ver P. And so this is so this is this Frobenius functor. So then lemma, important lemma. So this functor, of course, is not additive. But it turns out that the projection to here is additive. So the lemma is that this f is additive. And of course, twisted linear. So then it lands. Then it lands in the subcategory of vector spaces in here. So then it is the usual Frobenius. So it's additive and twisted linear. And then what happens is that in fact, if C is finite now, then what happens is the following: that often it lands in. So maybe I should say that it is in C1 times VRP because it's a twisted linear thing. Often it lands in some C hat 1 times VRP, where this C hat is a subcategory of C. So sometimes it lands into a smaller subcategory. And then you can iterate it. So you can define f squared. So f squared, so you start with C, you go to C1 times VRP, and then you go to C2 times VRP squared. But there is a functor from here to VRP, which is just tensor multiplication, so you get to C2 times VRP. So this is the square of f. And then you can cube it and fourth power and so on. And each time this component decreases in the Frobenius-Perron dimension, so size, until it stabilizes. And then when it stabilizes, so if it stabilizes, then Ostrik showed that this means that the dimension of C, which is the sum of squares of dimensions of all the objects in our field, is not 0. So it turns out that when it stabilizes, it is not what is called separable category. Separable. Dimension is not 0. But then if it is separable, then there is a theorem which we proved with Nikšić and Ostrik 15 years ago in the Annals paper, that separable category lifts to a category over p-adix in a unique way, in fact. So we have a lift C tilde in characteristic 0. But then by Deligne's theorem, C tilde is representations of a group. And it has a fiber functor. And then you have to use a descent theorem, which is actually was proved incorrectly in our paper with Nikšić and Ostrik. And I had to write a separate paper about this using this power reductivity, which I just mentioned, to correct that error. It's a really hard theorem that you can descend a fiber functor from characteristic 0 to characteristic p. So this means that if C is if this C is minimal, it doesn't decrease anymore, then it's representations of a group and it has a functor to vector spaces. And that way you end up just in this factor, which is VRP. So this is basically the idea. But it uses this notion of size, which only makes sense when it has finitely many objects. And so that's why this, and the lifting theorem and so on, which only work in the finite setting. So Ostrik believes that there should be a proof which is simpler and more along the lines of the proof of Deligne's theorem. But what we can prove, even in the non-semisimple case, so in the non-semisimple case, you can do the same thing. And there is this functor. And so we can prove, but in general, a functor from here to here is very much non-exact. It is not exact on the left or on the right. But, of course, a composite functor from C to here is exact if C is semisimple. And so what we can prove is that if you have a finite category, not semisimple, but the Frobenius functor is exact, then there exists a fiber functor to VRP, even for non-semisimple. Okay, so that's probably enough. No, I did not cover a lot of things actually, but